Okay, Assalamualaikum warahmatullahi wabarakatuh. Good evening, good morning, good afternoon, good night. And I, Irfan Ali bin Nazri and Nishaan Kumar anak lelaki Subramaniam going to discuss on SNPS on ITO. First is SRD pattern. From our raw file of ITO, put into Python, analyzed through Python, and then give experimental SRD pattern, and then we get the graph like this with Miller indices, the blue one, and then we got the peak where we set the threshold for 30% of the intensity, and we got the peak, and then from there we matching references with Material Project API open source, and we got the HKL, the Miller indices from ITO Material Project, and then the peak matching analysis, we got it all of that match, and the difference is slightly different, 21 degree and 24 degree for project material project. So there's a slightly difference, and this is due to the structure, crystal structure, and difference profile used in analysis by us and by material project, and then the X-ray diffraction patterns also quite different from the analyzed SRD pattern. Next is the crystal structure. From the data we have, we can get the T spacing by putting the HKL we get from the matching references, and then we get the lattice parameter, which is 9.0783 and strong, which is quite far, which is not so far, but it has uh, compared to the 10.39 from Material Project, which is slightly different due to HKL plans, and maybe there is some another elements or something that is contribute to the orientation to Q and plans, which is can be related to Black law and lambda to this base HKL sin theta, and we took it as 1 and lambda is 1.5 something, and then to this spacing, and then sin theta we got from the 2 theta from the SID. Crystallographic planes HKL 200, 220, 222, and etc. align with cubic, because when we sum up the 2 plus 0, we come with even number. 2 plus 2 plus 0, even number. 3 plus 1, we got even number too. Which is, if it is odd number, it will not has reflection due to the cubic. And that's all from me. Thank you.
Continuing from the earlier slide discussion, let's now focus on the structural and electronic properties of indium tin oxide, or ITO. Starting with its chemical bond, ITO is a solid solution of indium oxide and tin oxide. Within its lattice, indium ion and tin ion cations are surrounded by oxygen ion and ions, forming octahedral coordination. The bonding is predominantly ionic due to its large difference in electronegativity, but there is a partial covalent characters due to its orbital hybridization between the metal cations and oxygen cations. What makes ITO particularly useful is that tin ion substitution for indium ion introduces free electron, enabling N-type conductivity, which is essential for its role as a transparent conductor. Moving on to phonon behaviors, which is key to understanding ITO's thermal and optical properties. Phonons are essentially the quantized vibration of atom in a lattice. In ITO, they are calculated using density functionality perturbation theory, we observe both acoustic mode, important for heat transport, and optical modes interact with light. Notably, the absence of imaginary phonon frequencies confirms that the crystal is dynamically stable. However, the thin ion dopants introduces slight structural disorder which enhance phonon scattering. This contributes to In₂O₃ low to moderate. Let's now look at how electron behaves in In₂O₃ and how its band structure supports this. Due to the extra electron from thin ion substitution, In₂O₃ exhibits n-type conductivity. These electrons occupy the conduction band, making In₂O₃ a degenerate semiconductor. Its Fermi level lies within or close to the conduction band. The band gap, calculated to be 0.28 eV, is direct in nature. While small, it still defines this material's semiconducting behavior. The valence band is composed of oxygen 2p orbitals, while the conductive band is mainly from indium and tin 5s orbital. This electronic arrangement supports efficient charge transport while maintaining optical properties. Lastly, let's discuss thermodynamic stability. From the phase diagram, In₂O₃ has an energy above hull of 0.093 eV per atom, which means it's metastable. Although it's not the most stable configuration at 0 Kelvin, it is still potentially synthesizable, especially under non-equilibrium conditions like therm-therm deposition. The formation energy is negative 1.963 eV per atom, indicating that forming In₂O₃ from its element is energetically favorable. If it were to decompose, it will break down into a mixture of indium oxide and tin oxide, which align with its known binary oxides. That concludes our presentation on In₂O₃. Thank you for your time and attention. I hope you find it insightful.